Hello, everyone. Welcome to DemSum. It's great to see everyone joining us today for what will be an insightful talk that I'm sure will help inform the way we think about the doing of our work. Today's talk is co-hosted by the Center for Demography of Health and Aging, and Christine Schwartz will be introducing today's speaker. A quick note on the format for today's DemSum. Dr. Alexander is very happy to take your questions during her talk, so ask away. I'll be monitoring the chat as well as hands. So go ahead and raise your hand if you have a question, and I'll call on you. Unmute yourself, turn on your camera now so you can be present, or when you're asking your question, if your environment permits. Alternatively, if the online camera live stream is not working for you, please post your question in the chat function and I will relay your question on your behalf. I think that's it for formalities. At this point, then, I will turn it over to Christine to introduce our speaker. Thank you.
Great. Thanks so much, Catherine. I'm really pleased to welcome Monica Alexander to DemSum. Dr. Alexander is an assistant professor of statistics and sociology at the University of Toronto. She studies statistical demography, mortality, and health inequalities, and her research often uses non-traditional data sources. Monica's work spans a broad range of topics. For instance, she has a really nice paper that I encourage everyone to check out that's coming out in Demography on the average length of life for those who die in their first year of life, otherwise known as 1A0. To all you fans of life table notation out there. So check out that really cool paper coming out in Demography. She's also doing research using data from big crowdsourced online genealogies, has a project studying the impact of the Alaskan Permanent Fund dividend. So that's the closest thing we have to a basic universal income. And so she's looking at the effects of this on child maltreatment investigations in Alaska. So another really cool project. She also organizes Our Ladies Toronto, an online community of R users, and co-organizes a formal demography working group, which brings together demographers from all over the world. So we're really pleased to have Dr. Alexander here and learn more about her work and hear about Bayesian models and reconciling incomplete demographic data. Welcome.
Thanks very much, Christine, and thanks everyone for having me. It's a real pleasure to be here. I'm sad that I'm not actually in Madison. I was telling the students earlier that I have been to Madison once and walked around the campus, and it's a beautiful campus, even in winter, which is when I visited. So that's saying something given that I'm Australian. As Christine mentioned, I'm at the University of Toronto. I'm jointly appointed in statistics and sociology, but I'm a demographer by training. And today I'm going to be talking about how we can potentially use Bayesian methods to reconcile demographic data. And so the start of this talk is pretty general, talking about issues and what we could potentially do. And then the second half of the talk is talking about a specific example from my own work, looking at subnational population estimation. Okay. So demographers are pretty used to thinking about dealing with different sources of data and trying to make them all reconcile and match. A large part of demography is demographic estimation and getting really good estimates of sort of the fundamental indicators of populations and population change, like mortality, fertility, and migration. And usually these outcomes that we're interested in require thinking about data from one or more sources. Based on the data available, we might have a really good picture of what's going on in terms of drivers of population change. The data that we have might be quite complete, but it may have various sources of error. We may only have a partial picture in terms of like particular populations that we have data on or particular time periods, for example. or we just might not know anything at all, and we have to try and come up with demographic models that allow us to sort of infer what might be going on in populations where we don't have any data. So thinking about sort of the fundamental, one of the fundamental equations in demography, the population accounting identity, shown up here, this is just saying that the population in the next year is the population this year plus births minus deaths plus in-migrants minus out-migrants, right? So this is sort of our, our bread and butter as demographers. And thinking about this sort of process, if we had data on every one of these components, then demographic estimation as a field would just purely be an accounting exercise, right? We could just get all the components on the right-hand side, sum them up, and then we've got we know something about the population for next year. But the problem is, and sort of the core of, I guess, this talk is we usually don't have data on all these components. And if we do, there's sort of various issues surrounding those data. So, a big example of this is vital registration systems, where we get a lot of our information on births and deaths. They just don't really exist in a lot of countries worldwide. So in the US, they do. In Canada, they do. But thinking about many low and middle income countries, there's no sort of centralized civil registration system that records a population births and deaths. Thinking about migration isn't like, you could sort of get over the issues with births and death data, and then you come to migration and it's just like a whole new kettle of fish, really. Migration is hard because, it's not quite so easy to define. Who is a migrant depends on what your definition of migration is. There's short-term versus long-term, there's different geographic boundaries, internal versus international migration. And so it's hard to define and hard to measure, right? So usually countries are only interested in who's coming in, not necessarily who's going out, that sort of thing. And then thinking about even if we had data on the events that we're interested in, right? So the number of births, the number of deaths, or the number of migrants, for example, usually we're interested in rates. So comparing those counts of events to some sort of population at risk. And when we do that, usually the source of the data for the numerator is not the same source as the data from the denominator, and there can be different issues based on where the numerator is coming on versus where the denominator is coming on. So for example, issues with how race is defined, for example, is often different based on death certificates versus like population census counts, for example. So we have all these issues, which means that often we have to come up with demographic models by way of either like mathematical generalizations or sort of based on empirical regularities to try and deal with some of these data issues. So demographers are actually really good at this, and as a field, we have a long history of coming up with really cool ways of dealing with bad data, right? So the top sort of screenshot here, hopefully some in the audience recognize what this is. This is like what's generally known as the first ever life table. This is from John Grant's Bills of Mortality, written in 1665. I think I should have checked that. But basically he, looked at death registries in London and then decided that actually the probability, he tried to calculate, NQX, right, the conditional probabilities of death in each age group, and decided that they were basically constant across age. And so he came up with the first sort of life table, which is sort of shown there from a screenshot from that book. Another example, this picture on the left-hand side is a Hutterite family. So thinking about a lot of the work that came out of Princeton in sort of the 60s and the 70s, looking at historical population patterns in Europe, there's these indicators called the Princeton indices, which are looking at different types of marital and non-marital fertility. And the issue was that Ansley Cole was trying to solve was he wanted to look at age-specific fertility rates, but didn't have age-specific birth data. He just had total numbers of births, but he had the population age structure right. And so these Princeton indices sort of compare different aspects of the historical Europe population to data from the Hutterites, who are sort of known to have a really high fertility rates. And so coming up with these indices where we can compare fertility across groups with incomplete measures of age-specific fertility rates. And then the final picture here is just the front of the Cole-Demey life tables, model life tables. So these were, back in, if you studied demography in the 70s or 80s, this is sort of what you had. Everyone had a copy of this book, and you sort of looked up various, calculated various summary measures of mortality levels based on incomplete measures of, infant or child mortality, and then got a model life table based on this book. So this was based on a huge data collection, coming up with sort of key patterns of mortality for different regions of the world and trying to generalize those to imply life tables where we didn't have data. And so historically, demographic estimation as a field has been very good at this, but it's really been thinking about, okay, what can we do with the data we have? Coming up with models that are based on observing really strong empirical regularities, and then applying those models to populations where we don't have any data at all. But thinking about, as time goes on, we are collecting more and more data, right? So now we have DHS data for, a huge number of low and middle income countries that just didn't exist 3 decades ago. We have increasingly more interesting administrative data to study demographic outcomes. And also thinking about sort of more non-traditional sources like data from social media, data from other sort of, cell phones, other sort of electronic activity that wasn't designed for demographic research, but could potentially be useful in such fields. So we do have an opportunity to be sort of more data-driven than ever, right? So, but the problem is these data all come with their own sort of suite of issues. And so to really use them to the best of our ability, it opens up a whole new sort of can of worms, or if you're an optimist, a whole new research agenda in understanding, the different biases and the different issues with missing data and non-representativeness, and how we can best use these data sources. And so thinking about the classical approaches, demographic estimation traditionally was very deterministic, right? So we had all these different data sources. We have the population accounting identity. We know everything has to add up, right? So we have to try and make it add up. And there's the various sort of ad hoc adjustments that you make often when you're modeling population change over time. You just look at births and deaths, and then the residual is like migration. You sort of wave your hands and say, well, the rest has to be net migration. And so in these sorts of traditional approaches, I guess there's little or no propagation of uncertainty in the data, right? So we know that different sources of data have different sources of error. Right? There can be sampling error, there can be measurement error, there can be model-based error if you're fitting like a regression. And so there's all these different sorts of errors. They're hard to reconcile, and they're hard to reconcile all at once. And so my work and a lot of sort of work that's coming out of statistical demography at the moment is sort of trying to think about, okay, how can we reframe a lot of these sort of classical demographic approaches to be within sort of probabilistic frameworks, such that we can think about uncertainty more, measure the uncertainty, and try and account for it in demographic estimation. Sorry about the typo there. So this is all, leading into, okay, in particular, I use Bayesian methods, which are sort of a suite of statistical methods. And so I wasn't quite sure what the audience was going to be, so I thought that I would just give you a crash course in what Bayesian inference is in 2 slides. because obviously, you just need 2 slides to understand this stuff. It's totally fine. Okay, so Bayesian inference is based on Bayesian probability. What is Bayesian probability? It's one interpretation of probability. So if you're sort of used to running regressions and doing t-tests and doing hypothesis testing, that sort of thing, a lot of those sort of ideas are based on the frequentist interpretation of probability. This is the idea that if we do something enough times over and over and over again, and then count the number of times that something happened, divide it through by the total number of events, that gives us the true measure of probability. So it's this long-term frequency idea, right? So you flip a coin over and over and over and over again, and then you count the number of heads, divide it through by the number of flips, and that gives you the probability of a head. Bayesian interpretation is slightly different and thinks about probability as like a state of belief. And so you can think about, okay, before I even flip that coin, I think that it's probably unbiased. So I think that the probability of a head is 0.5, for example. So it's this, rather than being an objective like state of what happens after an infinite number of trials, you're thinking about your current state of belief. And so when you're thinking about the Bayesian interpretation of probability, we usually think about it in terms of the combination of what we know before we see any data and then what we see based on data, right? So this is a stylized version of Bayes' rule. What it's saying is, and you may have heard this before, the posterior probability is proportional to the prior probability multiplied by the likelihood. So what this is saying is the posterior probability, so the probability of an event happening or a parameter having a certain value, given we see some data, is proportional to the prior probability that we have before we see data, and then the probability based on of the data that we see given the parameter of interest. Right. So, but what does this actually mean when we're running regressions and stuff? How does this affect sort of the classical regression framework? So if we think about a linear regression model here, just a simple linear regression with one covariate, often what you may be used to thinking about is we're trying to get estimates of the intercept and the slope, the beta naught and the beta 1. We think about these as fixed but unknown quantities, right? So there's some true value of beta naught and some true value of beta 1 that we're trying to estimate. We don't know what they are, but we have some data, and conditional on the data we see, we come up with the best point estimate. And then if you sort of wave your hands and make some assumptions, we can actually write down a sampling distribution of our estimator and then do some statistical inference based on that. The Bayesian case is slightly different. Instead of thinking about, okay, there's one true value of beta naught and beta 1, we consider them to be random variables. So what does that actually mean? It means that we can now think about probabilities of certain values happening. So we can, before we see any data at all, we can say, well, actually, I think that maybe the value of beta 1 is likely to be in these ranges. And so we can assign prior probability to these parameter values, and then we can update that prior probability based on any data that we see, right? And so the resulting estimate of our parameters of interest here, they are the beta naught and beta 1, are a combination, like a weighted sort of average of our prior beliefs and the data. Okay. So how does this help us in demographic estimation? And I think that actually Bayesian methods are well suited to a lot of demographic estimation problems for a number of different reasons. So the first one is, I guess, the classical thing about Bayesian methods is that you have this sort of vehicle to incorporate prior information. So, and for a lot of demographic problems, we do have quite strong priors about what things should be based on, historical processes, based on biological or social processes. So there's a few examples on the screen here. So for example, when we think about age-specific mortality rates, for pretty much all human populations, we're really used to seeing that really strong J shape over age, right? So we have relatively high infant mortality, and then we have a drop, and then, it ends up sort of being pretty log linear over age once you get to adult ages, right? So this is we can be pretty sure that any sort of age-specific mortality curve in human populations will have that sort of characteristic shape. We know that peak migration usually occurs in working ages, right? We know that fertility rates are very unlikely to go above levels of high rate populations, right? So we have all this sort of information that, it makes sense that we should, that we could like incorporate this information in the form of prior probability distributions. The second reason is Bayesian methods allow for this better propagation of uncertainty. So I said before that the whole idea of Bayesian methods is that we're now treating the things that we're trying to estimate not as fixed things that are true but unknown, but themselves are random variables, right? So we might be interested in estimating regression coefficients, like, a Gompertz mortality model. We want to estimate alpha and beta, for example. We might want to estimate mortality rates, life expectancies. We can think about these things as random variables, and that allows us to assign probability to different values. Because of that, because we can write down a probability distribution, we can more easily think about different sources of error and what might be affecting likely outcomes. I've put here, there's an added bonus and I think this is actually an undersold bonus of Bayesian models, particularly for demographers, is that the way that you estimate things, you end up with a bunch of samples. And so you actually do your inference and get your uncertainty intervals on your parameters based on calculating things from samples. It's simulation-based inference. And because of that, it's actually really easy to get uncertainty around functions of things. So in a classical life table setup, if you're calculating life expectancy, even if you know the uncertainty around your mortality rates, it can be really hard to write down the standard errors around your life expectancy estimate, for example. But with Bayesian estimates, it's actually really easy. You just sort of take your samples and then you calculate life expectancy based on each sample, and then you get the uncertainty intervals based on the samples. So I think this is actually an undersold benefit of these methods. And then the last sort of thing that I want to mention is related to propagation of uncertainty, but it's sort of Bayesian methods that really lend themselves well to writing down things in terms of a data model, right? So we've got an outcome that we're interested in. So for example, it might be mortality rates, it might be population counts. We've got data on that, and we can sort of write down this, what we observe is a combination of the truth, which is what we're trying to estimate, plus some error. And then what goes into that error, well, we can consider different types of sources of error that go into that. So there can be sampling error, for example, if we're using a survey. There can be error due to non-response. There can be measurement error, that sort of thing. And it's sort of quite natural to write these things down and sort of incorporate all different types of uncertainty together. Okay, so I'm in classic Monica style, I'm talking a lot. So I'm not sure if I'll get through all my slides, but I'll try. Sorry about that. But now I want to talk about a specific example from my own work where we were looking at estimating populations at the subnational level. So the motivation for this work is sort of related to this idea I was talking before. A lot of countries, we just don't even know, we don't have a good idea of how many people live in different subnational areas, right? There's no sort of vital registration system. There are other sort of instabilities in these countries. And so even like getting the counts of, population groups of interest is kind of hard to do. But getting counts of number of people by demographic characteristics is super important, right? So we often want to turn like rates of disease or rates of something happening into numbers to get an idea of, like, how many vaccines we have to send to a certain area, for example. There are specific groups that are of particular interest. So I'll be talking about women of reproductive age, so women aged 15 to 49, that make up the denominator in so many health indicators. So fertility rates, maternal mortality indicators, contraceptive use, abortion-related indicators, that sort of thing. And so it's important to try and estimate these things even if we don't have good data. So the idea of this project was to try and come up with a cohort component projection model to be able to estimate these things in really data sparse settings. So thinking about cohort component projection models, they're based on the population accounting identity for each age group. They're actually really data intensive because you need counts by age for every single year to project forward. So often we don't have these in a lot of populations. And so thinking about population estimation and projection, people generally tend to fall back on simpler models like, linear interpolation or some sort of reduced form. But cohort component projection models are really informative because they tell you not only about population size, but also how components of population change are changing. So the goal of this project was to sort of come up with a cohort component approach that we could use to, so this was explicitly looking at women of reproductive age. We wanted to use data that was sort of broadly available across a wide range of countries, so it could be generalizable to different populations. So we were looking at women of reproductive age in Kenya. There's a link to the preprint up online. As of last week, so literally less than a week ago, I found out that this was accepted to Demography, so I'm very excited about that. So I guess it'll be out in, the next year or however long things take. Okay, so what have we got for Kenya? So Kenya has 47 counties, and that's sort of the level that we want to get estimates for. These are divided up into 8 provinces, and we have information. We have pretty good information from decennial censuses in Kenya. So that gives us what we're interested in. So county populations, counts by age group. And we can also get some information about migration from censuses. So the Kenyan census asks you something like, where did you live a year ago? You can sort of use that information to calculate raw counts of in and out migration based on counties. The other information that we have that we'll be using in the model is national level information based on estimates from the UN Pop Division's World Population Prospects. So WPP has estimates for national level population and other demographic indicators, so in particular mortality estimates for all UN member countries. So it's widely available. And so we'll be using these to get national level information. Okay, so what's the model? So just sort of a bit of setup here. So we're interested in estimating populations by 5-year age group for each age group between 15 and 50. So I'm going to introduce some notation. In particular, we're interested in estimating the true population in every age group, time period, and county. I'm calling these eta ATCs. What do we observe? Well, we actually have some observation of this thing. So this thing that we're interested in, county level population by age, I'm going to call the observations YI. Right, and so YI refers to the I refers to just the ith population, ith observation, and then every observation can be attached to a particular age group, time period, and county. There's a note here that sort of made things slightly more complicated. I probably won't go into it today because I won't have time, but there's an added complication with subnational stuff because your county boundaries are usually not stable over time, but people in health and policy planning want population estimates for the most recent county boundaries. So in terms of like going back historically when things are changing, it's kind of tricky. IFMs, which is wonderful and great, and thank you IFMs, is really, really useful in terms of trying to partially solve this, because they have, IFMs have made their own sort of harmonized districts, they're called, which are stable over time. So as well as publishing the micro level data based on the county level, which is what we're interested in, we also have this district level as well. Okay, so where are we going? So there's a whole bunch of things that we need to estimate with not very much data. So the thing that we're interested in are these true population counts by age, time, and county. So we need a process model to describe how these things are changing over time. Our process model here is essentially a cohort component model. Within that, we also need some sort of model for the drivers of population change, in particular mortality and migration. I can get into later why we're not looking at fertility, but I won't for the interest of time now. So we need a model for mortality and migration. And so this is sort of asking, like, how do these things change over time? And then we need data models that relates any data that we observe to the truth, right? So a few slides ago, I had this, we observe something and that's equal to the true outcome plus error. So this is our data model. So we can say, we can relate what we observe to the truth plus some error and make some assumptions about the error. And then in terms of this model, we also have a couple of constraints. We want the sum of the subnational population estimates to broadly match WPP at the national level. And we also want the sum of internal migrations to be close to zero, because people have to either in-migrate or out-migrate, and that should all be roughly zero. Okay, so in terms of a process model for the true population, it's essentially a cohort component model. So our true population in age group A, time T, and county C is the same cohort the year before, multiplied by the proportion of that cohort who survived through that age group, multiplied by the net migration rate, essentially. And then we have this additional sort of age, year, county multiplier that allows a little bit more flexibility in the model. So we have the gammas, which are our conditional probabilities of death. We have a net migration rate, and we have this other age time multiplier that we need to put models on these things to estimate. So you may have already sort of got this vibe, but there's a lot going on in this model. There's a huge amount of there's a lot of different components, because we've got decades of data. We've got however many, 18 age groups, 47 counties. And so, it's all centered around this sort of cohort component projection framework. And then we have our process models for our different components, right? So that's modeling what we think that the true underlying parameter is. And then at the top, we have these data models that relate what we observe to the truth. So there's a lot of different aspects here, and I'm already really out of time. So I'm just going to focus on what the mortality and migration components look like, and then I can talk about other stuff offline. So the mortality model, so we need an estimate for the conditional probability of death for every single county. We don't actually have any data at the subnational level on mortality. All we know is we have our national level mortality estimates. But what else do we know about mortality? The thing that I was talking about before, we know that there's this really strong pattern across age, right? We know that mortality generally, in the age groups that we're interested in, it generally increases over age. And so if we can find some way of sort of modeling those characteristic shapes and being able to sort of shift them up and down and twist them based on a particular county, that would be a pretty good place to start. And this idea is actually this is the same idea of what cold domain life tables do. You have a whole bunch of different life tables based on a reduced set of parameters. And so we have national level population schedules, mortality schedules for Kenya from WPP. And so we can use those national level schedules to get sort of the characteristic shapes. And these are sort of extracted using singular value decomposition, which sort of extracts like the main sources of variation across age and time. And then we can use those components that we get as the basis of a regression to pick up those characteristic shapes in mortality. So in particular, here's what, these three components is what we're using in the model. So the first one, these are all on the logit scale, so the y-axes are negative. So the first one is sort of the mean mortality schedule. The second one is the first sort of principal component that we're pulling out of the age by time mortality schedules, which just shows mortality improvement over time. And then the second component here has this sort of funny sort of V shape. And if you flip that, it actually ends up that that's sort of picking up HIV/AIDS mortality, which sort of peaked in Kenya in the early 2000s and affected women sort of, it had the highest effect of women aged in the 35 age group. So these are sort of our characteristic shapes, and we can use these as a basis of a regression. And then the regression coefficients allow you to sort of move these up and down and sort of weight them differently based on different counties. So that's what we're doing. So on the logit scale, we're modeling county level probabilities of death as a linear combination of those three components plus a county level intercept. And so there's different things going on in terms of how these coefficients are modeled as well. So we have sort of additional levels here that allow us to think about sharing information across space and time. But the general idea is just sort of a principal components regression model. Okay, so that's the mortality model, the piece. Now the migration piece. So unlike mortality, we do have some information at the subnational level. So we have this like question from the census, where did you live 1 year ago, that we can use to get observations of in and out migration counts. But even given that, it's still a pretty bit asked to estimate a separate in and out migration parameter for every single county, every single age group, and every single time point. And so what we did was we looked at the data and realized that actually the age distribution, so not the counts by age over time, but the age distribution of in and out migration is really, really constant over time. So I've got a graph here. So this is basically every facet here is a different district. And then every colored line is a different year. And then what's shown is it's the proportion of all in-migrants who are in those particular age groups, right? So you can see that it's actually really constant for most of the counties. These messy ones are the really small counties, so we sort of account for some of that based on sampling error. But in general, this is like a really good, really strong motivation to simplify the model for migration to assume that age distribution is constant over time. By doing that, we're all of a sudden having to estimate a lot less parameters than we otherwise would have. And so in particular, how we're modeling net migration, it's the sum of in minus out. We're modeling these things separately because otherwise you run into a lot of issues if you just consider net migration. So for a particular number of in-migrants and out-migrants, it's the product of, so for in-migrants, for example, the number in a particular age group, time period, and county is the product of the total number of in-migrants in a particular year and county, multiplied by the proportion of in-migrants that are in a particular age group. And so this thing is the age distribution, And that doesn't have a t index, meaning that it's constant over time. Okay, right. And then so again, we have we've sort of reduced our number of parameters. We still have to put some assumptions on these things, and we assume that we basically put some more models on these that again allows some smoothing over time. So we're assuming that changes in migration are pretty sort of smooth over time. Okay, and then I just wanted to mention part of the data model as well. So this is the bit that relates the observed population counts to the true population counts. So in particular, on the log scale, we're just assuming that the observed population count for a particular age, time, and year is centered at the truth, plus some error, where error is just based on sampling error, and that's based on the fact that we're using microdata from IPMS, which was just a 10% sample of the total census. So there's two lines here, and this is just related to that funny, I was mentioning we only have observations at the county level for 1 year, and then all the other years we just have observations at the district level. So we have to sort of define things differently based on the years. But essentially, we're just accounting for sampling error, and it's a similar setup for the migration observations as well. So this is obviously really simplistic. So we're just assuming the data that we observe, the only error that we have is based on using a sample. You can imagine all sorts of other errors that go on. I think the next step of this project is trying to validate some of the census data on where we potentially have better quality data, for example, from a HDSS site, where we can get some more information about sorts of maybe some of the types of undercount that we're seeing. Okay, right, so that's sort of just coming back to the model summary. So I talked about the mortality and migration components, and then very briefly about the data model. But the sort of idea is we have all these different components that are centered around this cohort component projection framework, but this is being fit in sort of a probabilistic setting where we're allowing for different types of uncertainty and getting a distribution of possible estimates of our true populations of interest, which is what we're interested in. Okay, so just to show a few results. So this is population by age and by year for 3 different counties. They're quite different in terms of age distributions and size. So I should say here that we had, going into the model, we had data up until 2009. And so the 2014 and 2019 are actually population projections based on the model. So you can see that the uncertainty around the projection, so the 2 pinkish lines is higher, and it's blowing out as you go further out. As projections, you know, that's what you sort of want in a projection. You're more uncertain about things further out in the future. And then you can see that there's sort of 3 different profiles here. So Nairobi is like really a special case. It's a huge population. And actually, there's so much in migration, you're getting this sort of peak population at sort of the 20-year-olds, because there's so many people in that younger working age group coming in that they're actually more than replacing based on mortality. Wajir is one that has a little bit more evidence of out-migration. And then Baringo is a relatively small county. So you can see that there's more, in general, there's more uncertainty around the estimates. Here's some example mortality curves based on the 3 counties of interest. So in general, Nairobi is much higher, estimated to be much higher. Wajir is relatively low, and Baringo is sort of, this is equivalent to about the national mean mortality. And then looking at migration, so we have estimates of the age distribution, so both in and out. So Nairobi has this really strong, sort of age pattern in migration, and our estimates here are relatively, the uncertainty around these is relatively small, purely because we're dealing with quite a large population, whereas the picture is less clear in the other two. And then finally, looking at total flows in both the in and out directions, again, we're getting much smaller uncertainty around Nairobi compared to the other two. And notice the flows here are just like enormous for Nairobi. So we're sort of projecting in 2019, in minus out leads to a net migration of about 350,000 people. Okay. So just to summarize then, this project was all about trying to come up with a way of essentially placing a cohort component projection model, which is sort of a classical demographic technique, within a Bayesian probabilistic framework. Cohort component projection models are really useful in understanding more about what's driving population change over time and what might happen in future. And it's a lot more informative than just sort of linear interpolation. It's really data intensive, so it's generally hard in data sparse settings, and particularly hard at the subnational level, because at the national level, at least you can usually wave your hands and ignore migration, but you really can't do that at the subnational level. And you saw with Nairobi, it's a really, really important driver of population change. And so we had hardly any data, but we have a really strong theoretical model, right? And so we can use that to sort of constrain what we think the true population might look like over time, and also constrain such that in terms of the estimates of mortality and migration that we're getting, they're plausible based on what we expect, given our sort of demographic knowledge. And estimating these in sort of a probabilistic framework avoids this sort of situation where we have like different data sources coming in and we're trying to reconcile them all in a sort of ad hoc way. And that's it. Thanks very much for listening. I hope you enjoyed it, and I'm happy to take any questions, and thanks for showing up. It's been really fun.
Wonderful. Thank you so much, Monica. This is a really rich presentation. And I see already a hand up. David Kaplan, go ahead and unmute yourself and ask your question.
Yeah, thank you very much. I presume you can hear me?
Yes, I can.
Okay, yeah, thanks very much for this great talk. I was really impressed that you could do Bayes in 2 slides. I'm not a demographer, but I do work on methodological developments within Bayesian statistics, so I'm familiar with Bayes. And one of the questions I had for you, because I'm not a demographer, is that my interests recently have been in the in what's, as you probably know, is referred to as multi-model inference. So not only do you deal with uncertainty in model parameters, you deal with uncertainty in the choice of models themselves. And what I was wondering was whether or not that made sense in the context of what it was that you were working on, particularly since your interest is in forecasting and projection, so that any given model that you might choose would not do as well, in some frequentist sense, interestingly enough, but would not do as well in some long-run prediction compared to, for example, stacking models together for the same outcome, or looking at model averaging as a potential possibility as well, although that has its own set of issues associated with it. So I was wondering if that question even makes sense to you, and whether you've considered it in this context. I'll turn off my mic. Thanks.
Yeah, no, thanks for the great question. I think so. In terms of forecasting, I can definitely say that people are looking at like model averaging as a way of trying to improve forecasting in demographic contexts, borrowing from different sort of time series literature as well. I think the question about when to use it and why it might be useful and maybe why it isn't useful is like what you're trying to get out of projections. So I think there's this like, this tension between, understanding versus like prediction accuracy, right? So I think maybe averaging a suite of models makes sense in terms of trying to get the best forecasts of populations as possible. And maybe that's what we want for, like, you know, if we're trying to like forecast how many vaccines we need to send to them. So maybe we just need a really, really good forecast. Maybe it makes sense in that situation. But then on the other hand, if we're more interested in like trying to understand why populations are changing, so for example, maybe we're trying to do projections in light of COVID, like trying to understand like what's going to happen to population. These sorts of models where we're breaking it down into the components and thinking about, okay, what could happen to migration, what could happen to mortality. I think if the goal is more trying to understand what might happen to these different components, maybe it's best to, like, you know, you lose a bit of accuracy based on model averaging, but you gain in sort of simplicity of understanding.
Yeah, it's sort of like a bias variance trade-off, basically. Yeah. All right. Thank you very much.
Thank you. Kelsey, I see your hand.
Yes, sorry, I am cat bound always. I can conceptualize some answers to this, but I'm just really interested in what you would say. So a lot of what we've talked about is either projecting kind of current data into the future or current data for current use. How do you think about this as applying to historical demographic projections?
Yeah, so that's a really good question. And so the neat thing about this sort of the cohort component models is that you can equally apply them for historical reconstruction. And actually, you know, there's a large sort of body of literature that does that. So a lot of the ideas in this paper were sort of inspired by another paper that looks at fertility reconstruction in different contexts. And so using a cohort component model to sort of go back in time to understand where we came from. And so definitely, and I actually, as another example, a project that I'm working on at the moment is trying to estimate stateless populations in various contexts. And we're looking at sort of these reconstruction ideas using a cohort component framework to try and reconstruct historical populations of Shona in Kenya. So we have really good survey data about the Shona population in 2019, and we have a census in that year as well. So we have some sort of like triangulation ability, and we kind of know a little bit about historically when the Shona came to Kenya and, like, you know, how many there were and that sort of thing, and maybe a little bit about their age and sex characteristics, but we don't know anything in between, right? So you can think about using these types of models to try and, instead of stepping forward, as you're saying, stepping back in time.
Great, thank you. Christine, go ahead and unmute yourself and ask your question.
Thanks so much for this talk. I think the answer to this will probably be, it's not an issue, but I was just wondering if when you have sparse cells, like zero counts in cells, does that present any special difficulties for these models?
Yeah, I think so. Zero, I mean, the short answer is zeros are always hard. Particularly with mortality, right? Because it's like, is it really that no one died, or is it just because we didn't see anyone? And so the nice thing about these sort of statistical models is that you can put in zeros and it doesn't necessarily estimate the answer as zero, but it still is difficult because often it's really hard to get like decent uncertainty around, you know, really low values and stuff. So the short answer is zeros are hard. We can still use them, but they're hard because often we don't know whether it's missing data or whether it's actually a true zero. This was a huge problem with another project that I was recently on, looking at maternal cause of death, and so, you know, there were sort of 6 key groups, cause of death groups that we're interested in, and one of them was abortion, deaths due to abortion. And so you can imagine that there's a huge number of zeros reported by national agencies. But thinking about, are these true zeros, or are these missing data, or are these undercounted, is a really hard question.
Thank you. Jenna, I see your hand.
Thank you, Monica. This was fantastic. So one of the questions I had was, it seems like a key reason to do this at the national level is we're trying to get good denominators for rates, right? And so I was thinking about the person who picks up your paper and converts those numbers into rates. And, in a traditional sense, often we use some kind of bound estimate to put around rates to construct a range. But when you're working on this and producing estimates with a range here, I was trying to think about how to convert that uncertainty into rate uncertainty, and whether you provide the outputs from this paper in a way that people do that.
Yeah, that's a really good question. I think the short answer is that we could. Like, I think if people are interested, then, if someone came to us and said, I want to calculate, I need denominators for a particular thing, can I have your estimates with uncertainty? We'd be like, sure, here you go. I think that that's probably not going to happen often. And you can more imagine that, if we publish our estimates, these are just another, they're another set of subnational population estimates that people could potentially use. And so how to think about, how best to use these and account for uncertainty for someone who's coming at it from not really, not being used to dealing with samples, for example. Maybe a good thing to do would be use our estimates and use estimates from the World Pop Project, and then see how different, the rate calculations are, and trying to understand uncertainty a little bit that way. But that probably didn't actually answer your question. I think the question is, could you use these to get uncertainty around rates? You could, yes, definitely. If I gave you samples, then you could get uncertainty around the rates. In the same way that I was saying, if I gave you samples of mortality rates, then you can calculate uncertainty around life expectancy. Yeah, you just play around with the samples.
Excellent, thanks. Catherine, can I ask one more question since no one else's hand is up?
Yes, and then I have one.
Oh, okay.
Carry on.
Okay. So quick one. It's something that comes up a lot is when we're thinking about doing any kind of forecasting. A question that that students raise a lot actually is, a lot of the places that we have really incomplete administrative data are also places that have a fair amount of instability politically and economically, and from an epidemiologic standpoint. And so, how do we deal with, or how do you deal with that? That's more straightforward. How do you think about the probability of unusual events that have unusual age parameters, so natural disasters, war, things like this?
Yeah, I think that's a really good question. And even thinking about COVID and population projections or any forecasting at the moment is that's hard enough, right? I think often, so I guess it gets to the distinguishing projections and forecasts, and I guess these are purely projections because we're just projecting forward what's happening in the past. In terms of making forecasts, the ability to sort of test a certain, you could use a model like this to say, okay, maybe I think this is going to happen to migration, what happens to population. You could use this sort of framework to test a whole bunch of ideas and get a range of possible population forecasts based on a natural disaster. Or ideally you would have another data source. So maybe there's cell phone, cell phone data that you can use to get an idea of outmigration. Maybe there's like, you can get something from social media data, maybe there's some other data source that you can combine with this sort of framework to get an idea of like what, putting at least some information in to try and get an idea of what's going to happen to population. I think that, it's always going to, in those sort of contexts, it's always going to be really uncertain, but like using this sort of framework to try and quantify like what are the possible ranges of what's plausible here and how can that possibly affect population is still useful.
Thank you. I have a question. It's actually many questions swarming in my mind, but it can be summarized, I think, in the question of how should I be thinking about the spatial unit here? And what I'm thinking about is you've got the county in the example that you shared with us today, right? You're looking at the county specific piece. So what I wonder about is the information that the county is or could be bringing to this process. And maybe even in this example that Jenna was just speaking to in your articulation of the difference between a projection and a forecast. And then thinking back to some of the data you're showing with the different, I think of them as like age signatures, and where the squirrelier ones are of course the small areas, because smaller areas are hard to get a handle on. So I'm just curious, within this framework, how should I be thinking about the spatial unit given what we know about spatial structures and data, and that there's repeated information or buried treasures of information that might be gleaned or might be screwing things up. So again, it's the big, all of that is the big question, is how should I be thinking about that spatial dimension when you're trying to estimate a place specific value?
Yeah, no, that's a great question. And I think like, well, if I understood correctly, I think like you could run one of these models and come up with estimates for every one of the 47 counties in a sort of systematic way, right? But then you might have a particular county that you can go, they have a certain, maybe they have a really good population register, maybe they have a HDSS where they get really good information on mortality, maybe that, so I think like this was sort of like this is a conceptual framework, and then based on different sorts of information you have about particular places, you could potentially hone in on those and incorporate those if you're interested in a particular place. I think more broadly, it gets at the sort of, this sort of tension between data and estimates, right? And so I'm making population estimates for a particular county using national level data, and often if you sort of go to that county, you might go to that county and say, hey, look, I've got an estimate of your population, it's this, and they might go, well, no, I don't believe that, because I have this Excel spreadsheet on my computer that says actually the population is this. And so there's sort of this tension between like, do we believe in complete data versus do we believe estimates? I think like actually a lot of these models and estimates from these models are most powerful when thought about as motivations to get better data, right? Because we're building these models because we don't have any data, but hopefully part of doing that is like, showing people that, okay, if we could collect better data, we would have a better picture of what's going on. And I think that goes not just for this paper, but, for IHME models and like, the sort of UN models, that sort of interpreting those as a mechanism to drive change in terms of better data collection is really, really important, because first and foremost, I think what's important is to try and get better registration systems in countries, and hopefully that they can be seen as a motivation for that.
Thank you. We're just about at time. If folks we probably have time for one more remaining question. if there's another out there. All right, with that, I just want to, this has been just a really rich talk and a great discussion that's followed, and I appreciate it very much, and invite folks to continue the conversation with Dr. Alexander over email. Next week, DemSem will meet in person, and you'll get to see whether I still have a back of my head. So we will be meeting in person at present, and together with CDHA, CDE is hosting Dr. Hans-Peter Kohler, who's a demographer and a sociologist at the University of Pennsylvania, and also the co-director of Penn's Population Aging Research Center. Many of you are familiar with Kohler's work. He's going to be sharing some work from his longstanding and very impactful research program on health in Malawi. But before we part ways today, please join me in thanking Dr. Alexander again for a really informative and actually pretty inspiring talk here today. Thank you so much.
Thanks very much for having me. It's been really fun.